Okay, I think we better start our class now. Okay, so
Okay,
where do before what page? Can you please advise me? After general, I'm sure it is after general. Okay. The derivative, fixing, implicit. Okay. Then we have so before we discuss on general, and after that we discuss on exponent and inverse. Okay, okay, so we start with a new topic that is derivative of exponent, okay, and inverse trigonometrics. Okay, so we have here the y is equal to x, a linear graph, which is the graph of y equal to x. Okay, so we know that if we have a function y, okay, so the inverse function of f, okay, so this is y equal to f of x. The inverse function of f here, which is denoted as f super index -1 of x, is the reflection. It is the reflection of the graph y about this line y equal to x. Okay, so if this is the graph of y, then the reflection is about is also can be called as mirror. Okay, so mirroring about this graph y equal to x, then we will get this new graph, and this new graph is the inverse of the graph y. Okay, so that is inverse. So that's why the inverse of exponent function e to the power of x is the logarithmic of x with the base e. And if you observe carefully, okay, you know that the graph of y equal to ex looks like this, isn't it? So this is ex, and this is a new line. This is a line y is equal to x, and the inverse of the exponent of x is the logarithmic function. Okay, it is ln function. This is ln x, which is the log of x with the base e. Okay, so they are inverse to each other. In other words, they are reflected. This graph is reflected about y equal to x. Okay, and then what? let's say you have, I think you have learned this before during your secondary school. Okay. So let's say you have fx equal to x to the power of 5 plus x plus 1. Okay. Show that f is 1 to 1 on interval from negative infinity up to infinity. So f prime of x is fx to the power of 4 plus 1. Okay. Which is always greater than 0. Why we know that is because x to the power of 4 is always greater than 0 or equal to 1. Equal to 0. If x is equal to 0, then the whole thing becomes 0, and what is left is 1. 1 is always greater than 0. But then if we have x negative, x to the power of to the power of 4 will give it a positive number. This one will become positive. A positive number plus 1 will give you also a number which is greater than 0. And it is real, so obviously it is real. For all real numbers x, f prime of x is always greater than 0. Okay, so from theorems 3.31 says that 3.31, this one, okay, if we have f prime of x is greater than 0, then f is 1 to 1. Okay, f is 1 to 1. Okay, next B, find the formulas for the derivative of f inverse. Okay. So y is equal to, so let's denote y equal to f inverse of x. Differentiate x equal to f of y is equal to y to the power of 5 plus y plus 1. Okay. And then we can use implicit differentiation. So d dx of x. Okay. So we start from here. So x is equal to this side here, to the right hand side. Okay, we integrate with respect to x, and we get the left hand side will become 1, and for the right hand side we have here 5y to the power of 4, and right after we differentiate with respect to x, since this is a variable in terms of y, then we have to write dy dx after we write this. Okay. And then for this one, we differentiate y, we get 1. Okay, and then we write dy dx. For this one, it is okay, give you constant. Okay, and then you make dy dx as the subject, then you get this. Okay. And we cannot solve x equal to y to the power of 5 plus y plus 1 for y in terms of x. So we leave the expressions. It means that we cannot express y to the power of 4 here in terms of x. Okay. And then for C, compute f inverse, derivative of f inverse when we have x is equal to 1. Okay. So dy dx when x is equal to 1, we know that dy dx is this one. Okay, it is this one. So we just substitute. Okay. We should just substitute x equal to 1, but somehow there is no one. There is no variable x in these expressions. Okay. So we need to know the value of y, which is f inverse of x at x equal to 1. Okay. So y to the power of 5 plus y plus 1, okay, is equal to 1. And then we will get, solving this, we will get y equal to 0. Okay. So y to the power of 5 plus y is equal to 1 minus 1, which gives you 0. Okay, and then you solve this for y, you get y equal to 0. So you substitute here y equal to 0, then you get the derivative of f inverse when x is equal to 1. Okay. So that's it. Okay, now we go to derivative of exponential functions. Okay, so uh, the the formula for the exponential function for b to the power of x, okay, the derivative of b to the power of x is given by b to the power of x multiplied with ln b, okay. But when we have e to the power of x, if we differentiate e to the power of x, we will get ex. Why is that? It is because ln e is equal to 1. Okay, if we substitute here, if we write here, this one, it is equal to ex ln e. But then ln e is equal to 1. So that's why we will get the derivative of ex is itself. Okay. 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 Now use formula 7 and 8. Okay. To compute the following problem. Okay, the derivative of 2 to the power of x, just substitute the b here is equal to 2. Okay, just substitute and then we got that. We got 2x ln 2. What about this one? This one will be this one can be solved by using a chain rule. Okay. For the second one, okay, so we have e to the power of negative 2x, okay. So we have to find the derivative of this, okay. So you have to denote u as negative 2x, okay. I think I need to use one note. d dx e negative 2x. d dx e negative 2x. Okay. So y is equal to e negative 2x. We are asked to find dy dx. We substitute u is equal to negative 2x. So in other words, this one, y of x is e to the power of negative x. So this is y of x. But for y of u, that is equal to e to the power of u. Okay. And then we know that we are asked to find dy dx, but our dy is now in terms of u. So it is dy du multiply with du dx. Okay. So dy du, okay, you differentiate y with respect to u. Okay. So the dy du will be equal to eu. Okay. And then from here, the du dx, it gives you what? It is equal to negative 2. So du dx is equal to negative 2. So you just substitute, and then you got dy du is e to the power of u, and then you multiply with du dx, which is negative 2. Okay, so this is still not final because you have to substitute what is u? So it is e to the power of negative 2x multiply with negative 2. This is the final answer for dy dx. Okay, negative 2e to the power of negative 2x. Negative 2e to the power of negative 2x. Oops. Okay, for the third one, e to the power x to the power of x to the power of 3. Okay. So y is equal to e to the power of x to the power of 3. So you want to find dy dx. What is dy dx? And then we substitute u as x to the power of 3. Okay, so our dy dx is equal to dy du multiply with du dx. Okay, and then if you have u equal to x to the power of 3, then your y is equal to e to the power of u. So from here, what is du dx? Your du dx will be 3x to the power of 2. And then for this one, the dy du is equal to e to the power of u. And then you substitute it here. You substitute it here. Your dy dx is equal to dy du, which is eu, multiply with du dx, multiply with 3x squared, okay? And then you replace the u in terms of x. So you have 3x squared e to the power of x to the power of 3. Okay, so that is your answer. X squared e to the power of x to the power of 3. Okay, next one. Next one, e cos x. Okay, e cos x. So y is equal to e cos x. So here you have u is equal to cos x. Okay. So you have dy dx is equal to dy du multiply with du dx. Okay. So if your u is cos x, then the du dx will be negative sine x. Okay, and then if you denote u is equal to cos x, it means that your y is actually equal to eu, isn't it? Okay, so you differentiate y with respect to u, you will get itself. Okay, so this one will be negative sine x multiplied with e to the power of u. So for cos x, you will get negative sine x multiplied with e cos x. Okay, so that's it. So that is your final answer. Negative sine x e cos x. Okay, negative sine x e cos x. Okay, next, example 4. Example 4, you have d dx x squared plus 1 to the power of sine x. So for this one, you have to take ln for both sides of the equations. Okay, so x squared plus 1 to the power of sine x. X squared plus 1 to the power of sine x. So this is your y. This is your y. Okay. So what we do here, we take a ln for both sides. Okay, so what we have is ln y is equal to ln of x squared plus 1 to the power of sine x. But from the properties of log, you know that this one sine x can be written in terms of sine x multiplied with ln x squared plus 1. So this one can also be written as sine x ln x squared plus 1. Okay. So what else? Okay. So and then we differentiate both sides with respect to x. Okay. Okay. It means that we use implicit differentiations. Okay. So we differentiate both sides. So d dx of ln y is equal to d dx of sine x ln x squared plus 1. Okay. You differentiate ln y in terms of x, it gives you 1 over y, and then you write dy dx. Sorry. And then you write dy dx. What about the right hand side here? The right hand side, for the right hand side, you have to use product rules. Okay. Where your u is sine x and your v is ln x squared. Okay, you have to use product rules. Okay, so your u here is equal to sine x and your v is equal to ln x squared plus 1. Okay, and then you have to find u prime and v prime as well, because the right hand side of this, the derivative of this is equal to u prime v plus v prime u. Okay, so what is your u prime? So u prime is easy. So u prime here is equal to cos x. What about v prime? So v is already known, which is this one, plus v prime. What is v prime? How are you gonna differentiate this? We know that the derivative of ln, okay, will give you 1 over something, isn't it? But it is difficult for this case. You have to use chain rule.
Yeah.
For x squared plus 1. Okay, so you already have notation for u, the v as well. What about now we use s? Is it okay? Okay, so let's denote s as x squared plus 1. Okay, so you want to find v prime. So v prime is obviously equal to dv dx, because this is in terms of x. Okay, so dv dx, it is now in terms of s. So your v here is equal to ln of s. Okay, so dv dx is equal to dv ds multiply with ds dx. dv ds, you differentiate ln s with respect to s, you get 1 over s. ds dx, it gives you 2x. Okay, so the answer will be 2x divided by x squared plus 1. Your s is x squared plus 1. So this is the answer. So this is v prime, so you have to substitute it here. Okay, so u prime, okay, let's use this color here. Okay, so u prime is cos x. The v is ln x squared plus 1 plus v prime. V prime is this one, 2x divide by x squared plus 1. 2x divided by x squared plus 1. Okay. And then you multiply with u. So your u is sine x. So that is your final answer. Cos x ln x squared plus 1 plus 2x divided by x squared plus 1 multiply with sine x. Okay. But that is for wait. But that is for 1 divided by y multiply with dy dx. For you to get dy dx, you have to transfer 1 over y to the right hand side. To the right hand side of the equations and make dy dx as the subject. Okay. Any question? Any questions regarding this problem here?
Tak ada puan.
Huh? Okay, huh? Everything.
No.
Okay.
Okay.
Doktor.
Good.
Okay, Doctor.
Okay, good. Okay, next. Okay, now we go to the derivative of the inverse trigonometric functions. Okay. So you have what here? Derivative of the inverse trigonometric function. So normally this is called arc sine. Sine to the power of -1 is actually the inverse of the sine function. But we normally call this as arc sine. I call this as arc sine of x. Okay. And then okay, let's start from here. Let's say you have y equal to arc sine of x. Okay, so obviously your x will be equal to sine y. Okay, so if you have y equal to arc sine of x, then x is equal to sine y. Okay, and then you differentiate both sides of the equations. In other words, you take implicit differentiation. Okay, then you got this one. Okay, you differentiate x with respect to x, you get 1. You differentiate sine x, you get cos y. Since you differentiate with respect to x, you have to write down dy dx. Okay, and then you make dy dx as the subject. You get dy dx is equal to 1 over cos y. Okay, but then you know that the y is equal to sine of x. So write down here sine of x in replace of y. Okay, so that is your dy dx. So cos of sine of x give the illustration that sine of x, okay, is actually theta. Okay, so it is an angle. Okay, so let's draw a triangle here. So denotes the sine of x as the angle. Okay, yeah, sine of x. Okay, and then wait, cos of x from the formula that you have learned before. Ka, so for cos it is ka. Ka. Huh? Is it ka? I think ka. So tua, right?
Oh.
So it is ka.
Sokah tua.
Oh, so kahtua. Okay, I think this is correct. So kahtua. So we want to use the information from kah. Okay, so kah for cos theta, it is adjacent divided by hypotenuse. Okay, adjacent divided by hypotenuse. Adjacent divided by hypotenuse. That is your cos. Wait, so the dy dx is equal to the dy dx is equal to this one. Is equal to 1 over cos of theta. Okay. Since it is adjacent divided by hypotenuse, 1 over adjacent divided by hypotenuse. So this is actually hypotenuse divided by adjacent. So your hypotenuse is equal to 1. So that's why you get here 1. And adjacent is square root of 1 minus x squared. Okay. So this is the reason why you got dy dx is equal to this. Okay, and then the d dx of sine of x, okay, since this is y is equal to sine of x. Okay, so d dx of sine of x is equal to 1 over square root of 1 minus x squared. So it is from here. So this is for x, and this is what if we have to apply chain rule. Okay, so this is the formula for the derivative of sine of x. But let's look at here. Why do you have sine of x be the angle? The hypotenuse is equal to 1. The opposite is equal to x, and the adjacent is equal to square root of 1 minus x squared. There must be a reason on why we draw this kind of triangle. So let's think about it. Okay. So we have a tangent. Sorry, we have a triangle. Sine x. Wait, now I'm figuring out why do we have this triangle. Okay, I know there must be a reason, but I cannot remember. Yeah, let's sort this out. Any idea on how we got the triangle? How do you get the value for the hypotenuse, the adjacent, this adjacent, and the opposite? Okay. So opposite. Okay, I know now. It is from these expressions. So you know that x is equal to a sine x. So sine y. Okay. Sine y. Wait. Must be from somewhere here. Wait. X divided by sine. So opposite divided by hypotenuse. So sine of y. Wait, sine of y. So sine of y is equal to, if y is the angle, from here it is so, SOH. Sine of y is equal to x. So x is actually x divided by 1. So opposite, so is opposite. O divided by H. So opposite divided by 1. So this is the reason why your hypotenuse is equal to 1. Your opposite is equal to x. Okay. So this is the reason why we draw this this triangle before we got this. since you know the hypotenuse, you know the opposite, you can get the adjacent by using Pythagoras theorems. Okay. So what is the Pythagoras theorem? Pythagoras theorem says that the opposite is equal, the opposite plus the adjacent, opposite squared plus adjacent squared is equal to hypotenuse squared. So that is Pythagoras theorems. So if you have C and you have B, you should know A. Okay, from the Pythagoras theorems. Okay, so let's say you have here C. C is equal to 1. 1 squared is equal to x squared, and then you don't know the value for adjacent. Okay, so let's denote this as A squared. Okay, so A squared is equal to 1 squared minus x squared, and for A, just take the square root of this. So square root of 1 minus x squared. So that's why you get the adjacent equal to square root of 1 minus x squared. Okay, so you can do the same thing for arc cos. Okay, so this is for arc sine. So for arc cos, you can use the same methods and get the formula for arc cos as given by this. Negative 1 over square root of 1 minus x squared. Okay, and this is in terms of u if you have chain rule. For the arc cos of x, it is just negative 1 over square root of 1 minus x squared. Okay, let's see example 5. Okay, find dy dx if y is equal to arc sine of x cubed. So here you have to apply chain rule. Okay, so the u is x cubed. So y is arc sine of x cubed. Y is equal to arc sine. Arc sine of x cubed. So this is the questions. The questions ask you to find dy dx. Okay, so by using chain rule, you can denote u as x cubed. So this one is equal to arc sine of u. Okay, so the dy dx is equal to dy du multiply with du dx. Okay, so your du dx is equal to 3x squared. Okay, 3x squared. And then we have here y is equal to arc sine of u. Arc sine of u. So what will be the dy du? So we have to find dy du. If y of u is equal to arc sine of u. Okay, so let's look at the table of what we have got before. The d dx arc sine of x is equal to this one, 1 over square root of 1 minus x squared. Okay, so so here dy du is equal to 1 over square root of 1 minus x squared, right? Okay. 1 minus u squared. Okay, because this is in terms of u. So y of u is equal to arc sine of u. So dy du will be equal to 1 over square root of 1 minus u squared. So your dy du will be equal to dy dx is equal to dy du multiply with du dx. So dy du is this one. So 1 over square root of 1 minus u squared. Okay, and then you multiply with du dx, which is 3x squared. Okay, but now replace everything which is in terms of u, so that it is now in terms of x. So 1 over square root of 1 minus, so what is u? It is x to the power of 3. X to the power of 3 multiply with to the power of 2. And then you multiply everything with 3x squared. Okay. And then here it will becomes x to the power of 6. So it is square root of 1 minus x to the power of 6. Okay. Square root of 1 minus x to the power of 6. And the numerator is 3x squared. The numerator is 3x squared. So this is the final answer. Okay, so any question? Any questions on how to do this? Anyone still do not understand? Okay, what about B? What about B? Secant of EX. So we still have to use chain rule here, and then the arcsecant can be obtained from this one. Arcsecant, the formula for the derivative of the arcsecant. Okay. So the questions is for y equal to arcsecant of what? Of EX. Of EX. Okay. Before that, I think it's better if we write down the formula for the derivative of arcsecant. So if we have y equal to arcsecant of x, then the dy dx is equal to, that is equal to 1 over absolute value, 1 over the absolute value of x. Okay. 1 over absolute value of x multiply with x squared minus 1. Okay. So this is the derivative. If we have a derivative of y for y equal to arcsecant of x. Okay, so we want to use this formula here. Okay. So let's use chain rule. So for the chain rule, you substitute u equal to ex, okay? So your y is now equal to arcsecant of u, okay? So your dy dx is equal to dy du multiply with du dx, okay? since y is equal to secant of u, then the dy du will be this one. But instead of in terms of variable x, here we will have in terms of u. So it is equal to 1 over absolute value of u multiply with square root of u squared minus 1. Okay, u squared minus 1. And then you multiply with du dx. So what is your du dx? If you have u equal to u ex, if you differentiate u with respect to x, you will get itself. Okay, so it will be e to the power of x. So this is your final answer. After you replace the u as ex. Okay, so this one is equal to 1 over absolute value of ex square root of ex to the power of 2, so e to x minus 1, okay, and then you multiply with ex. Absolute value of e to the power of x is actually equal to ex. Is it? Is it so? Wait, no, it is not. So it stays like this, okay? So for B, wait, why it can solve? We have arcsecant of u. This is absolute value of u, absolute value of ex. This one should have absolute value of e to the power of x. Oh, e to the power of x is always equal to absolute value of e to the power of x is always equal to ex. Why is that? It's because we know that from the graph of the exponents, it is always positive. It's always positive. It will never equal to negative value. So this one is also equal to ex. Since it is equal to ex, we obviously can cancel out this one and this one. Okay, so what is left will be 1 divided by square root of e to the power of 2x minus 1. Okay, so is it okay? Any questions up to this example 5? Are you still with me?
Yes.
Okay, ah? Okay, can we,
Okay, Doctor.
Doctor.
okay, boleh faham, eh? Can you understand this topic?
Okay,
Okay,
doctor.
Doctor.
Okay, good.
Okay, Doctor.
Let's continue. Let's continue with the next topic. So this is related rates. Related rates is the application of the chain rule. Okay. So let's look at the example. So let's look at example 1. Suppose that x and y are differentiable function of t and are related by the equation y equal to x cubed. Find dy dt at time t equal to 1 if x is equal to 2 and dx dt is equal to 4 at time t equal to 1. Okay. Wait. Okay. So we have equation y equal to x cubed. And then the questions ask us to find dy dt at t equal to 1. So this is the question. Okay. if we have the information that dx dt is equal to dt is equal to 4 at t is equal to 1. Okay, dx dt is equal to 4 at t is equal to 1. Okay, we want to use chain rule. Okay, so we have y equal to x cubed. So from the chain rule, we have dy. The questions want us to find dy dt. So we want to find dy dt. So dy dt is equal to dy dx multiply with dx dt. Okay. So the dy dt at t is equal to 1. Sorry. The dy dx can be obtained from this one. The dx dt when t is equal to 1. So the questions ask for when t is equal to 1. Okay. When t is equal to 1. So wait. This is dy dt. This one. What is given as is dx dt, which is this one, which is equal to 4. Okay. So this is equal to 4. This one. The dy dx, you differentiate x. When you differentiate y with respect to x, you get 3x squared. And the questions give you that x is equal to 2. You just substitute x equal to 2 here. Then you get 12 multiply with 2 to the power of 2. So 12 to the multiply with 4. So the answer should be 48. Okay, so it is 48. This is the final answer. Any question? Yeah, so I hope that you can understand that. Okay, now let's look at example 2. We have oil spill. From ruptured tanker spread into a circular pattern whose radius increase at a constant rate of 2 feet per second. Okay, so how fast is the area of the spill increasing when the radius of the spill is 60 feet? So the radius of the spill is 60. 60, so means that the R is equal to 60. Okay, and then it is also given that oil from a ruptured tanker spread in a circular pattern whose radius increase. Radius is increasing. Radius is increasing with the rate, with a constant rate. When we talk about rate, it's differentiating with respect to time. So the dr dt is equal to 2 feet per second. Okay, this is R. 2 feet per second. 2 feet per second. Okay. And then it is in terms of circular patterns. So circular patterns, we are dealing with A. So A, when we have circular patterns, is A is equal to pi R squared. Okay. And then the questions ask you for how fast is the area of the field is increasing, and the radius is 60 feet. Okay. So the questions ask you for dA, how fast. So it means that dA dt. We are talking about the rate of the area. Okay. So we are the questions ask for dA dt when R is equal to 60. So this is the questions. So you know that A is equal to pi R squared Okay. And dt is equal to dA dr multiply with dr dt. Okay. dA dr multiply with dr dt. So you differentiate A with respect to R, you get 2 pi R. Okay. You get 2 pi R, 2 pi R. And then the dr dt is given, which is 2 feet per second. Okay, so you multiply with 2. Okay. And then we know that the questions ask you for R is equal to 60. So just substitute 60 here. So 60 multiply with 2 multiply with 2. So 120 multiply with 2, 220. So the answer will be 240, right? 240 pi. So that is the answer. Wait. 240 pi. Okay. Pi feet squared per second. Okay. If you convert pi, if you substitute pi equal to 3.1142 something, then it will give you this. Okay, but I think this is already a final answer. So that is your dA dt when R is equal to 60. Okay, so any question? Is it clear? Or is it too difficult for you to understand? Okay, I hope it is still manageable for you to understand. Okay. Okay, I think all the other examples, example 3 and 4, you can do it at home, and it still use the chain rule, just the application of the chain rule that we have learned before. Okay. Okay, let's continue with the local linear approximation. Okay. Okay, here you have what? You have y is equal to f of x naught plus f prime of x naught multiply with x minus x naught. So this is actually from the equation of the line. Okay, so this is the equation of the line. So we know that from the equation of the line, we have y minus y naught, okay, divided by x minus x naught is equal to m. And since m is equal to f prime of x naught, then you can also write it as y equal to f of x naught, okay. The y naught is f of x naught. Okay, you can wait. Yeah, this is correct. So this is fx. I think we have to write in terms of this fx minus f of x naught divided by x minus x naught is equal to f prime of x naught. Okay, so fx is equal to y. So fx is equal to y, which is equal to f of x naught. If we transfer everything to the right hand side, we will get f of x naught plus f prime of x naught multiply with x minus x naught. It's the same. It's the same thing as this equation of the line. Okay, so this is the equation of the line, which is can also be written as this equation here. Okay, but what we can say is fx, the approximations of fx here is approximately equal to the right hand side of this. It is before it this is y, not f of x naught. Okay, why this is possible is because for the values of x near x naught. Okay, so this is the key here. For the values of x near x naught, okay, for the value of x, okay, near x naught. So let's say this is your x naught, okay, and your x is somewhere here, okay. The slope of this, the slope of the tangent line, okay, will be what we call this, wait, so this is your x naught. So let's say you have x naught here. So this is your x naught. Okay, for x close enough to x naught, then we can have this approximation. This approximation 1. If it is not close enough, so let's say the x is here, then we cannot say that fx is approximately equal to fx naught plus f prime x naught multiply with x minus x naught. Why is that? Okay, so let's look at example so that it is easier for me to explain. Okay, find the local linear approximation of fx equal to square root of x at x naught equal to 1. So how do we draw the graph of square root of x? Okay, so we have the graph of square root of x. Square root of x. So y squared will be like this. Should be something like this. Okay, so this is the graph of square root of x. At x not equal to 1. So let's say you have x not equal to 1 over here. Okay, find the local approximation, linear approximation to approximate square root of 1.1. Okay, so square root of 1.1, it means that your x is equal to 1.1 and your x naught is equal to 1, and this is close enough, and it means that you are able to use this formula in equation 1. If let's say the questions ask you for the approximation of 5 square root of 5.1 and the x naught is equal to 1, then you cannot use this approximation for equation 1. Okay, instead you have to change the x naught to 5 for square root of 5.1. Square root of x naught is equal to, let's say you have square root of 5, square root of 5, and square root of this one is square root of 5.1. Your x naught is square root of 5. Okay. For this one, it is okay. But if your x naught is equal to, let's say, 5, and this is square root of 1.1, then you cannot use. Okay. Okay. So the formula is given by this. F of x is approximately equal to f of x naught plus f prime of x naught multiply with x minus x naught. Okay, f prime of x naught, you have fx is equal to x to the power of 1/2. Okay, so your fx is equal to x to the power of 1/2. So by using power rules, you can get f prime of x, which is equal to 1/2 x to the power of negative 1/2. Okay, so 1/2 multiply with 1 over square root of x naught. Okay, and then you have here f of x naught, which is square root of x naught. Okay, multiply with x minus x naught, which is this one. Okay, and then your x naught is equal to 1. Your x naught is equal to 1. Okay, so just substitute x naught equal to 1, so you get 1. Okay, plus 1/2 square root of 1. Okay, square root of 1, you get 1. Multiply with x minus x naught is equal to 1. So x minus 1. So the approximation for the square root of x, when x is equal to 1.1, okay, can be solved by using this equation. Okay. So when x is equal to 1.1, square root of 1.1 is approximately equal to 1/2 1.1 minus 1, which give you 1.01. How can you confirm this answer is close enough? Is by using your calculator. You can press your calculator in finding the value for the square root of 1.1. Okay. So this is the graph for square root of x. At x equal to 1, we have the line, the straight line, okay, which is y is equal to 1/2 multiply with x minus 1, okay. So if you look closely, you can approximate the value which is lies on the graph, on the blue graph, as from the graph of the straight line, if they are close enough. But if they are not close, so let's say when x is equal to 3, they are not close enough. But for x which is close enough to 1, they are still acceptable for you to say that the approximations are quite close for the graph of the blue line and the purple line. Okay, but please make sure that the x naught and the approximation of x is close enough. In this case, the square root of 1.1 here is when the x is equal to 1.1, it is close enough when we take x naught is equal to 1. Okay? Okay, now, what if the questions ask you for the linear approximation for x, for let's say, wait, I'm thinking about the questions. What if the questions ask you for the approximation of 5.1? How are you going to solve this? Can you please do it in 5 minutes? How are you going to solve when you have square root of 5.1? Of course, you can check with the calculator what the calculator says about this. And how you're going to use a local approximation, local linear approximation in order to approximate this square root function. Sorry, this square root of 5.1. Okay. Any volunteer? Anyone? Okay, I give you 5 minutes and I'll pick one to explain. Okay, 5 minutes to settle this problem. For square root of 5.1. For 5.1, you have to take your x naught to be equal to 5. Okay, you cannot take x naught equal to 1. So here, you have this equation. This is the original equation. Okay, you substitute here 5, and then you get another equation for this one, and then you substitute. Okay, for 5.1. Okay, so that is how you do it. Okay, I give you 5 minutes. Okay, so any volunteer? Any volunteer to solve square root of 5.1? Anyone? Amira Usna, want to try? Amira Usna? Are you with me actually? Let's pick another name. Nuraida, how about Nuraida? Do you want to say something? Please explain to me how you're gonna solve. Are you actually with me in this class? Okay. I'm afraid you just join the meeting room, but then go somewhere else. Hello. Hello. No one want to volunteer. Okay. Let's look at the questions. So we have here square root of x. Okay. Square root of x is approximately equal to the square root of x naught. Okay. Plus 1 over 2 plus 1 over 2 square root of x naught multiply with x minus x naught. Okay, so this is our equation. Okay. So before that, can you please press your calculator and find the square root of 5.1? What is the value of this by using your calculator? What is square root of 5.1?
Doctor, you will get 2.258.
Sorry?
2.258.
2.258. Okay, so this is the almost exact value for the square root of 5.1. Okay, now we want to approximate by using when x not is equal to 5. Sorry, yeah, 5. When x not is equal to 5. Okay, so the square root of 5.1 is approximately equal when the square root of 5. This is not okay because we don't know the value when we have square root of 5. I think that you better change to, let's say, 4.1. Okay? Can we change to 4.1? Let's change to the questions to 4.1. Okay, so the
So you get 2.025.
wait,
Okay.
4.1, square root of 4.1 4.1 is equal to 2.25.
2.025.
Okay. Okay. Square root of 4.1 is approximately equal when we take x naught is equal to 4. Okay. So square root of 4 plus 1 over 2 square root of 4 multiply with x minus 4. Okay. So square root of 4 is known here. So square root of 4 is known, which is equal to 2 plus 1 over 2 multiply with 2. So we have 4 here. And then here you have x. X is 4.1. So 4.1 minus 4. Okay. So square root of 4.1 is approximately equal to 2 plus 4.1 minus 4 divided by 4. So 0.1 divided by 4. Okay. So what is the answer for this? 0.1 divided by 4. It's not
2.025.
it's not as difficult as to get the square root, the value for the square root. What is 0.1 divided by 4?
0.025.
0.025. Okay, you plus with 2. So the answer will be 2.025. Is it approximately equal to this one? When you calculate by using calculator, it is. So that's why the local approximation is valid whenever the x is close enough to x naught. But you cannot let's say you have x naught here is equal to 4.1 and you use x naught is equal to 2. That one is not okay. You have to choose the x and x naught which are close enough. Okay? Is it okay? Is it okay?
Okay.
But it depends on the value of f.
Okay.
In this case, the value of f is square root of x. Sorry. Yeah. We have fx equal to the square root of x. But if you have fx equal to something else, then you have to differentiate and get a new equation. This new equation. Okay? So is it okay? I hope so.
Okay.
Any question? No. Okay, now let's continue with the next topic, L'Hopital rule. We have learned this before. L'Hopital rule can be applied when you have 0 over 0 or infinity over infinity. Okay, you cannot use L'Hopital rule when you have other values. So let's say infinity divided by 0 or 0 divided by infinity or 1 divided by 2. You cannot use. It is only usable for you to use when you have 0 over 0 or infinity over infinity. Okay. Okay, so let's say let's see example 1. So limit of x squared minus 4 divided by x minus 2. Okay, when x is equal to 2. When x tends to 2. If you substitute in these expressions, when x is equal to 2, you will get what? You will get 0 over 0. So you can use L'Hopital rule. L'Hopital rule, you have to differentiate the numerator as well as the denominator. So this one is limit x tends to 2 for 2x divided by 2. Okay? Sorry, 1. Okay? And then you substitute once again. X is equal to 2. So the answer will be 4. So this is the final answer. Okay? The final answer is 4. So if you don't want to use L'Hopital rule, you might want to simplify these expressions. Okay? So x to the power of 2 minus 4 is actually x minus 2 multiplied with x plus 1. You divide, sorry, plus 2. You divide with x minus 2. X minus 2 can cancel out with the x minus 2. What is left is x plus 2. Is this correct?
Yes.
Okay, then you substitute limit x tends to 2 here, you will get 4. Okay, it will give you the same answer. Okay, for example 2, let's look at example A. Sine 2x divided by x. So when x tends to 0, sine 0 is equal to 0. You divide with 0, 0 divided by 0. You can use L'Hopital rule for this. So cos, you differentiate sine 2x, you will get 2 cos x. Okay, the limit x tends to 0. Okay, 2 cos x divided by 1. Cos x, cos 0 give you 1. So the answer is equal to 2. The answer is equal to 2. Okay. And then for B, okay, for B, 1 minus sine x divided by cos x. One minus sine x divided by cos x for the limit x tends to, I think, pi over 4, is it? Sorry, pi over 2. Okay, so you substitute when pi is equal to, sorry, when x is equal to pi over 2 in these equations, in this expression, sorry. So for the graph of sine, you have something like this. Okay? So this is 2 pi, and this is pi, and this is pi over 2. Okay? So when x is equal to pi over 2, the sine of pi over 2 is equal to 1. So this is 0, and cos of x for the graph of cos is something like this. Okay? So this is 2 pi, this is pi, okay, and this is pi over 2. So cos of pi over 2 is 0 as well. So we can use L'Hopital rule, okay? And then you differentiate 1 minus sine x. Okay, you got negative cos. Okay, so this one is equal to the limit of the limit for x tends to pi over 2. Okay, and then here you have negative cos x. You divide with the derivative of cos x. It's negative sine x. Okay, so negative cancel out, right? So cos x, pi over 2, cos x. Cos pi over 2, it gives you 0. Okay. And then sine pi over 2, it gives you 1. So 0 divided by 1. Okay, so the answer will be 0 divided by 1, which is equal to 0. Okay, so 0 divided by, the answer will be 1. Okay, any questions? Okay, I think you can do the other example. They are just the same. Okay. And then let's look at the next type, which is infinity divided by infinity. Okay, before we have mostly 0 over 0, but now we are about to solve for infinity divided by infinity. Okay, let's look at example 3. Limit x divided by ex as x tends to infinity. Substitute, you will get x equal to infinity and e to the power of infinity. Okay, so the exponent is something like this. When x goes to infinity, the e infinity will be infinity. So this one will be infinity as well. Okay, so this one is equal to the limit x tends to infinity. Okay, you differentiate the numerator, it gives you 1. You differentiate the denominator, it gives you itself, which is ex. And then you substitute, it will give you 1 over infinity, which gives you 0. Okay, 1 over infinity is, if you take the limit, it will give you 0. So the answer will be 0. Okay. And then for ln x divided by cosecant of x. As x tends to 0 plus. Why the questions ask you for 0 plus? Because for ln x is only defined for x positive. So this is the graph for ln x. It's only defined for x positive. It doesn't define when x negative. So that's why this is valid for x tends to 0 from the right hand side only. There's no graph which is defined for x tends for x negative. Okay, so that's why for x tends to 0 from the left hand side, there is no graph. Okay, but for this side, it is okay. Okay, and then what? Ln x, if you substitute x equal to 0 from the right hand side, it will give you negative infinity. Cosecant of x, what is cosecant? Cosecant is 1 over sine, right? 1 over sine. Sine of 0 is equal to 0. 1 over 0 will give you infinity. So the answer will be infinity over infinity for this. Okay? So you differentiate numerator and denominator. 1 over x is for the derivative of ln x. And cosecant of x, if you cannot remember, then what you have to do in order to differentiate this? You have to use what? What method? What rules?
Quotient rule.
Yes, quotient rule. You can use quotient rule and get this. Cosecant x multiply with cot x. Okay? And then you substitute x tends to 0 here. I hope you already got the answer after that. If still not enough for you to get the answer, let's say this one also give you, let's say, infinity over infinity, then you can continue to differentiate the numerator, divide by denominator. Okay, is it okay? For this case, the last limit is again is in terms of infinity divided by infinity. So this one here, it still give you infinity, and the denominator is still give you infinity. So you continue with this with the derivative. You take this derivative here, 1 over x squared. Okay? Cosecant. the last limit in 4 can be written as what? Negative sine x divided by tangent. So in this case, it express this one in terms of this. So limit here sine, so sine x, tangent x, and this is 1 over x. Okay. Somehow it stopped with the L'Hopital rule, but try to simplify these expressions. Okay. Limit tangent x. This one I know. We have seen it before. Sine x divided by x as x tends to 0 is equal to 1. Okay. This is also from L'Hopital rule. Sine x is equal to 0. You divide with 0. Okay. So you differentiate, it give you cos x divided by 1. And then you substitute. Cos 0 is equal to 1. 1 divided by 1, it gives you 1. So that's why you have 1 here. Okay, but then the answer, you multiply with 0, it gives you 0. So the answer, the final answer is 0. So that is how you do it. If you cannot simplify, then what can you do for this? Can you apply L'Hopital rule once again? 1 over the derivative of 1 over x will be 1 over negative of 1 over x squared. Okay. And what about this one? It may be difficult because you have to apply product rules for this one. It will be complicated. Okay, so this is a better way, which is by trying to simplify it. Okay, and since you know that the limit of sine x divided by x is obviously equal to 1, then it can be simplified. Okay, so any questions? Is it clear? Okay. Anyone want to ask questions? Anyone? No? Huh? Okay, good. Okay, now intermediate form of type 0 multiply with infinity. Okay, example 4. So limit x ln x as x tends to 0 plus. Okay. If you in order to use a L'Hopital rule, it must be in terms of rational function. It cannot be in terms of multiplication. So it's better, in order to use L'Hopital rule, it is a must for you to transform this expression here so that it will be written in terms of rational function. So x ln x is actually equal to ln x divided by 1 divided by x, or it is also equal to x divided by 1 divided by ln x. Okay, so it is either these two. Okay, so from these two, you can then apply L'Hopital rule. Okay, is it clear? Okay, so we have what? If we substitute x tends to 0 here, you will have 0, and this is infinity. 1 over infinity will give you 0. So the answer will be 0 over 0. So you can apply L'Hopital rule. L'Hopital rule for this. Okay, this is 0 over 0. What about this one? Ln infinity. Ln 0, sorry, ln 0 will give you negative infinity. 1 over 0 give you infinity. So infinity over infinity. So obviously you can apply L'Hopital rule as well. Okay. So ln x divided by 1 divided by x. You differentiate ln x, you get 1 over x. You differentiate 1 over x, you get negative 1 divided by x squared. And then you simplify this. You simplify this, you get negative x. As x tends to 0 plus, this one will be 0. So this is the final answer. Okay. Okay, then we have infinity minus infinity. Like before, I've always mentioned that infinity minus infinity is not equal to 0. Okay, we have to find the value of that if we are able to do that. Let's look at example 5. Okay, limit x tends to 0, 1 over x minus 1 over sine x. Okay. In order for you to apply L'Hopital rule, let's express this in terms of rational function. So you have to multiply this. It is cross multiplications. Okay, so sine x minus x, and then you divide with x sine x, and then you substitute x tends to 0 plus here. So 0 minus 0, it gives you 0, and then it divide with 0, multiply with sine 0, give you 0 over 0. So it is L'Hopital rule. You can apply L'Hopital rules. Then you differentiate numerator, it gives you cos x minus 1. And then in order for you to differentiate x sine x, you have to use product rules. U prime v plus v prime u. Okay. So you differentiate x, you get 1. You multiply with sine x plus you copy the x and then you differentiate sine x, which is cos x. So after that, you substitute x equal to 0 in these expressions here. In this expression. Once again, it gives you 0, I think. Is it? Cos 0 is 1. So 1 minus 1. You divide with sine 0. Sine 0, which is 0. Plus 0 multiply with 1. It gives you 0 over 0. Okay? So once again, you apply L'Hopital rule. L'Hopital rule. You differentiate. You got negative sine x. You divide with derivative of this. So cos x plus this one you apply product rules. Product rules, you get cos x minus x sine x. Okay, and then you substitute x equal to 0. You get sine 0 equal to 0. But then for the denominator, it is not 0. So the final answer will be 0 because 0 divided by something, any constant except for 0, it gives you 0. But if let's say you still got 0 for the denominator, then you still have to apply L'Hopital rule. Okay. I hope it is clear. Okay. Now, intermediate forms of type 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. Okay. What about this one? 1 plus sine x to the power of 1 over x. X tends to 0. Okay. So actually, in order for you to solve this, it is easier if you take ln for both sides. If you take ln for both sides of the equation. So ln y is equal to ln 1 plus sine x to the power of 1 over x. And then you use the properties of the logarithmic function. So this one can be returns in front of the ln x. So 1 over x ln 1 plus sine x, okay? And then here, it is now in terms of rational function. Okay, and then you take the limit x tends to 0, both sides, okay? So ln 1 plus sine x divided by x. This one, 0, sine 0, it gives you 0. Ln 1 is 0 as well. If you look at the graph, it intersects at x equal to 1. Okay, so ln 1, it gives you 0. 0 divided by 0 here. So it is possible for you to use Pista Rule. Okay, and then what? Limit ln y x tends to 0. Once again, you want to apply Pista Rule here. So you apply Pista Rule, but it is not straightforward. You have to use a chain rule here. So what is your u? Your u will be 1 plus sine x. Okay? So your u here will be 1 plus sine x. Okay? If you apply this substitution, then you will get cos x divided by 1 plus sine x. And then you differentiate the denominator, you get 1, and then you substitute here. Cos 0 is 1, divided by 1, so the answer will be 1. The final answer is 1. And then it is still not final yet, because what we find here is the limit for ln y. We take the limit for both sides of the equation before. We are asked to find the limit of y instead of ln y. So in order to get the limit of y, okay, so if you want to find the limit of y as x tends to 0, you have to take exponent both sides. So exponent of ln y give you y. Okay, for this one, it will give you exponent of 1. It's actually exponent of 1. Okay, now this one is exponent of limit y. It is equal to y. Okay, and for the right hand side, it is e to the power of 1. That's why it is e. Is it clear? Any questions? Any question? Is it clear? Okay, good. Okay, let's look at the next one. Okay, the next one will be a new topic. So I think let's stop here and continue next week for the next for the topic 4, for the new chapter 4, the derivative in graphing and applications. Okay, so thank you very much. It's raining here as well, so I'm not sure if the internet connections is okay or not. It's raining quite heavy over here. So thank you very much. I will stop the recording now. Okay.